This is a recording of some exercises from 3.2. We're going to look at the two groups of problems looking at when things are and are not differentiable. Let's start with this problem number one. We're asked to find the right hand and the left hand limits to show that it's not differentiable at this point P. And then we'll find all the points where f is not differentiable. If we start with this idea that we have a right hand limit, which is going to be the limit as h approaches 0 from the left hand side, this will be the left hand limit of f of x plus h minus f of x all over h, and in this case that limit is equal to the limit as h approaches 0 from the negative side of x plus h squared minus x squared over h, which is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x all over h. These x squares cancel. That leaves us the ability to pull out an h, giving us 2x plus h over h. These h's cancel, and when we use the substitution process, we end up with 2x. So if that's the case, as we're approaching this point, the derivative, the slope at p coming from the right, is going to be 2 times x, and x is 0, so the left hand derivative is equal to 2 times 0, or 0. Now the right hand derivative, this is a line. All of the slopes along this line are equal to the same thing, which is 1. So the right hand derivative as we approach 0 is equal to 1. These two derivatives, the right hand derivative and the left hand derivative, do not match. Therefore the derivative does not exist at p. And this would be considered one of those places where a function has a corner and derivatives don't exist at corners. So that's problem number one. Okay. Problem number two, the left hand limit, the left hand derivative is equal to 0. As we approach p going this way, all the slopes along here are 0. Left hand derivative is equal to 0. The right hand derivative is equal to 2 because it's linear, and all of the slopes along that linear segment is going to be 2. Again, the two derivatives don't match. Therefore the derivative at p does not exist. We say that it's not differentiable at p. For problem number 3, let's take care of the easy one first. The right hand limit, or the right hand derivative, which is based on the limit, is equal to 2. This segment is linear, the slope is 2, the right hand derivative is 2. What about this limit, the left hand limit? Well, let's do a quick calculation. The limit as h approaches 0 of f of x plus h minus f of x all over h, which in this case is equal to the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Can't use the substitution process yet, so now let's multiply both the top and the bottom by the conjugate, which is going to be x plus h minus x times square root of x plus h plus x square root of x, and that's all over h times the square root of x plus h plus square root of x. Continuing on, we end up getting the limit as h approaches 0 of x plus h minus x all over h times the quantity square root of x plus h plus x. Those x's cancel, those h's cancel, leaving me the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. We can use the substitution process here, and we end up with square root of x plus the square root of x, or 1 over 2 root x. Now, since we're interested in the left-hand derivative at that point, the left-hand derivative therefore ends up equaling 1 over the square root of 1 over 2 times the square root of 1, or 1/2. Again, we notice that the right-hand derivative and the left-hand derivative do not match, and therefore our conclusion is that f is not differentiable at p. Problem number 4. In this case, the left-hand limit, the left-hand derivative at p, looking at p, is going to be the easy one, left-hand derivative, and that is this linear function has a slope of 1 all the way through it. The right-hand one will have to do the limit as h approaches 0, in this case from the positive side, of f of x plus h minus f of x all over h, in this case, which is going to be the limit as h approaches 0 from the positive side, and it's going to be 1 over x plus h minus 1 over x all over h, which I like to rewrite as 1 over h times, and then I find the common denominator of x times x plus h, and that's going to be x minus quantity x minus, or x plus h. Continuing over here, the limit as h approaches 0 from the positive side of 1 over h times x minus h all over x times the quantity x plus h. These x's cancel. The negative h on top cancels with the h in the bottom, leaving me a negative 1 on top. And now we have something which I can use the substitution process on, and I end up with 1 over x squared. What is the value then of the right-hand derivative at 1? It'll be negative 1 over 1 squared, or negative 1. Hey, the left-hand derivative is 1, the right-hand derivative is negative 1. They don't match, and therefore our conclusion is f is not differentiable at p. So there's problem number 4. Okay, in problem number 5, we're going to ask on this closed interval, on the closed interval D, which is given right here, where are the points differentiable? Now, we're looking for spots where there are cusps, where there's corners, where there's discontinuities, where there's vertical tangents. I don't see any of those attributes on problem number 5. So where's it differentiable? It's differentiable on the entire interval from -3 to 2. B, where is it continuous but not differentiable? It is not. If it's differentiable anywhere, there's no spots where it's not differentiable, and there's no spots where it's continuous nor differentiable. So we got 2 no's for continuous but not differentiable, or neither continuous nor differentiable. In problem number 6, again, I'm looking for corners, cusps, vertical tangents, and discontinuities. I don't see any of those things there, so where is it differentiable? It's differentiable on the entire interval from -2 to 3. There are no spots where it's not differentiable, and there's no spots where it's not differentiable nor discontinuous. Problem number 7, where is it differentiable? Well, it's going to be differentiable from 3, and then as we come up here we have a discontinuity, so up to 0 but not including 0, and then from 0 to 3. So there's where we are differentiable. Where are we continuous but not differentiable? Well, I don't see any vertical tangent, cusps, or corners, so there is no place where I'm differentiable, continuous but not differentiable. See, neither continuous nor differentiable. That's going to happen at x equals 0. The discontinuity makes it not differentiable, so it is not differentiable there. Alright, on to 8. On this one, where is it differentiable? Well, I can see that we can start and we get differentiability from -2. We got a corner there, we got a discontinuity there, and we've got a discontinuity there. So how about from -2 all the way to 1, but not including 1, union with 1 to 0, sorry, -1, -1 to 0, not including 0, unioned with 0 to 2, union with 2 to 3, including 3. Now you can see they wrote the same thing down. They have this same answer from 0 to 3, but exclude or except for the spots that I've mentioned: -1, 0, and 2. Except, can't even spell except. Alright, where is it continuous but not differentiable? That is at x equals -1. We have continuity, but the corner makes it not differentiable. And then where are we neither continuous nor differentiable? That would be at x equals 0 and x equals 2. Right. Problem number 9. Where do we have differentiability? Well, it looks like we have differentiability for all the values from -1 to 2, except for at 0, where we have a what looks to be a vertical tangent. B looks continuous there, so it sounds like at x equals 0 we have continuity but not differentiability. And then C, we don't have any spots that are both discontinuous and not differentiable. So there's no spots that meet that criteria. Lastly, in problem 10, where are we differentiable? Well, it looks like we're differentiable on the entire interval from 3 to -3, except for these spots where we have these cusps. So except for x equal -2 and x equal 2. What kind of different or what kind of not differentiable situation do we have? It's continuous but not differentiable at those 2 points. So C would be, there are no places where it's neither continuous nor differentiable. And that's problems 1 through 10 from the 3-2 exercises.